Hello everyone, myself Dibyendu Chowdhury, Department of EC, Haldia of Technology, West Bengal, India. Today I discuss about the Varactor Diode. Varactor Diode basically a diode which is myself Dibyendu Chowdhury, Department of EC, Haldia of Technology, West Bengal, India. Today I discuss about the Varactor Diode. Varactor Diode basically a reverse PN junction whose capacitance can control with the reverse applied voltage in control manner. So first we start with the PN junction. PN junction is formed with the two semiconductor region, two opposite doping region, P type and N type. P type concentration are Na, and in case of N type the concentration are Nd. We assume that both regions are doped uniformly. So here this junction is basically called metallurgical junction. Here PN junctions important characteristics is they rectify, allow current to flow easily in only one direction. When we join the P and N region, then the concentration of the electron in N side and concentration of the hole in the P side is very high. Due to the higher concentration of carriers, holes are moved or diffused from the P side to the N side, and electrons move from N side to the P side. At the time, at the junction, there is a Na negative charge or bound charge are accumulated in the P side, negative charge accumulate in the N side, positive charge accumulate, which is called phase charge region. Due to the phase charge region, there create a electric field which is the direction from positive to the negative. So due to electric field, there is also a force at the edge of the depletion layer or phase charge layer. This layer also called the depletion layer. In the edge, diffusion force for the hole and electric force on the hole is cancel each other. In either side, in N side, also the force due to the diffusion of the electron and for the electric field force of the electron is neglect here. So in the phase charge region, the distribution of the charge and the electric field and the potential is like this. So here distribution of the charge carrier, this is positive charge distributes here and negative charge here. Similarly, electric field distribute at the phase charge region, or we can say in depletion region, where we see the electric field is maximum at the metallurgical junction. So here the distance from the metallurgical junction, if we consider it is 0, from the metallurgical junction to the edge of the depletion layer is xn at the N side and minus xp at the P side. If we see here that this distance is nothing but a width of the depletion layer. Width of the depletion layer. So if we find out the distance from metallurgical junction to the edge of the P side, that is xn up to xn, and metallurgical junction to the edge of the depletion layer at the P side, that is minus xp, then we can find out the W. So here phase charge density are defined like that: rho x is equal to minus E Na, where Na is the acceptance density or concentration at the P region and Nd is the concentration at the N region. So P rho x is equal to E Na at this region minus xp less than x less than 0. That means this point, and rho x is equal to End 0 less than x less than xn. That means this region. So at the x is equal to 0, the number of negative charges per unit area in the P region is equal to number of positive charges per unit area in the N region. So we can write NaXP is equal to NdXN. So we can determine the electric field and potential distribution from the Poisson's equation. This is the Poisson equation. From this equation we can find out the potential and electric field also. So in previous slide we see that the potential distribution is like this, where it at the edge of the depletion layer in the N side at xn, which is nothing but a Q V B I, where VBI is called the built-in potential. So this potential expressed by this equation, where VBI at xn is equal to E by twice epsilon s Nd xn square plus Na xp square. So from this equation and this concept, we can find out the value of the xn and xp. When we find out the xn, we replace xp from this equation, that is Ndxn by Na, and when we find out the xp, then we replace xn in terms of xp, that is xn is equal to Na xp by Nd. So from these equations we can find out the distance, that is xn and xp. Xn we express by this equation, which one we get from the previous discussion, and xp is this one. If we add xn plus xp, which is nothing but a w, w is here width of the depletion layer or pressure region layer or transition layer. So if here we find out the W of the depletion layer. So now we discuss about the junction capacitance, PN junction capacitance. PN junction capacitance two types. One is depletion capacitance, another is diffusion capacitance. Depletion capacitance is depend on the dopants, and diffusion capacitance depend on the free carriers charge, both charge. And depletion capacitance is appear due to the reverse bias voltage, and diffusion capacitance appear due to the forward bias voltage. So here depletion capacitance sometimes is called the junction capacitance, and diffusion capacitance is called the charge storage capacitance. So here in this lecture we are very much interested about the diffusion capacitance. So if we apply the reverse bias voltage, then the width of the depletion layer is modified, where VBI plus VR. VR is nothing but a applied reverse voltage. VBI plus VR. So if we find out the capacitance of the junction when we apply the reverse voltage, if we increase the reverse voltage or decrease the reverse voltage, basically the change the reverse voltage, then the depletion width also change, because we see W is equal to this equation. From here we can find out that the change of the width, that is dxp in this side and here dxn, the change of the reverse voltage with applied VR, plus del VR, this changes. This changes, due to the changes we can find out the capacitance C is equal to dq by dVR, where dq is the differential charge, and dq we can define by End dxn is equal to Ena dxp. The change of xn and change of xc we can find out. If we derive this equation, then we can find the dq. So we see that we know xn expressed by this equation. From the junction capacitance is C is equal to dq by dVR is equal to End dxn by dVR. So in this case we put this xn and simplify it, then we get this term. Okay, so here C is equal to this term, where we can say C is proportional to the inversely proportional to the VR. This one. So exactly the same capacitance expression is obtained by considering the pastel region extending into the P region XP. So we simplify more the capacitance equations. So W we know, this one is the W, where W is proportional to the VR. VR is the reverse voltage. If VR is increase, W also increase. Where capacitance is, if VR is increased, then capacitance decrease. It is inversely proportional. So we simplify C with this equation, then we get C is equal to epsilon S by W, which is nothing but a equation of the parallel plate capacitor. So we know in parallel plate capacitor C is equal to epsilon S by D, where D is nothing but the distance between two plates. So this is D. So two plate capacitor. So finally, this capacitance is called the junction capacitance, which is denoted by Cj is equal to C bar dot A. A is the cross sectional area of the PN junction. So here we find out the capacitance value of the junction when we apply the reverse bias voltage. And now on this concept, we can say the Varactor diode is a reverse bias PN junction whose junction's capacitance can be varied with the applied reverse bias voltage in a controlled manner. The term Varactor is derived from the words variable reactor. It is also known as varicap, meaning capacitance. So here we see when VR is at 0, then capacitance is maximum. If we increase VR means reverse voltage, then width of the diffuse layer also increase and capacitance is decrease. So the capacitance can be controlled by using different doping profiles such as abrupt, linearly graded and hyper abrupt doping profiles. It can also be controlled by the size of geometry of the diode. So here we consider the three type of doping profile, that is linearly graded, where M is equal to 1, abrupt M is equal to 0, and hyper abrupt M less than 0. So here we particular value we consider, that is M is equal to minus 3 by 2. So in this case, the general doping distribution can be expressed for one-sided heavily doped junction as follows. That is this one. Okay. So XDX is equal to AX to the M, where the M is vary for the linear graded and abrupt junction and hyper abrupt junction. We can solve again by the one-dimensional Poisson equations, by these equations, where this equation is integrating twice with the boundary condition, that is V is equal to 0 and V is equal to VR plus VBI. So at V is equal to 0, that means this is the metallurgical junction, and at V is equal to W, VR plus VBI is nothing but a width of the depletion layer, that is W. In this case, we consider the one-sided PN junction. This is heavily doped, this side, and then this side, P plus N. So due to this boundary condition we apply here, we get the W width of the depletion layer for this case, that is epsilon s m plus 2 Vbi plus Vr by Ea whole to the power 1 by m plus 2. From this equation we can say that W is proportional to the Vbi plus Vr whole to the power 1 by m plus 2. So we know W, we can find out the capacitance also. Junction's capacitance dq by dV, which expression this one. So from this expression we can say Cj proportional to the Vbi plus Vr whole to the power minus 1 by m plus 2. So for abrupt junction, we can find out the Cj. Cj is proportional to the 1 by root over Vbi plus Vr. Because we find out here Cj is proportional to the Vbi plus Vr whole to the power minus 1 by m plus 2. We put the value of m. We put the value of m and we put the value of m is equal to 0. Cj is equal to 1 by root over Vbi plus Vr. If we put the value of 1 for the linear graded junction, then we get Vbi plus Vr 1 by 3. And in case of hyperabrupt junction, we consider here 3 value minus 1, minus 3 by 2 and minus 5 by 2. So for this case, in each case, for the minus 1 Vbi plus Vr, minus 3 by 2 Vbi plus Vr whole to the power 2, minus 5 by 2 Vbi plus Vr whole to the power 3. So using this concept, we can determine so here Varactor diode symbol and equivalent circuits where Rs is the series resistance and Cj is called the junction's capacitance. If we consider the m is equal to minus 3 by 2 and for this case n is equal to 2, n is nothing but a m plus 2, where this Varactor is connected to an inductor L in a resonant circuit. The resonant frequency varies linearly with the voltage applied to the Varactor. So from here we get omega r is equal to 1 by root over L Cj, the general equation. So this is proportional to the 1 by root over Vr minus n, where we put Cj. Cj value is put here. So from the Cj value here, minus n is nothing but n is value is 2. If we consider the m is equal to minus 3 by 2, so then we get it is Vr. Omega r is equal to Vr. That means it is linearly proportional. So when we vary the Vr, frequency also change. That's why the statement is here. For this case, n is equal to 2 when this Varactor is connected to an inductor L in a resonant circuit. The resonant frequency varies linearly with the voltage applied to the Varactor. This is the one of the applications. So these are the applications of Varactor diode, FM radio and TV receivers, self-adjusting bridge circuits, adjustable bandpass filters, very low noise microwave parametric amplifiers, tuning of LC resonant circuits in microwave frequency multipliers, voltage control oscillators, frequency and phase modulators. Thank you all, and these are the reference.